Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark, and in this part we're going to begin a study of the Dirac equation, which is the foundational equation of relativistic quantum mechanics for the description of the electron and other spin 1/2 particles. So now we're going to begin introduction to the Dirac equation. It's an amazing equation with unbelievable consequences, and it's really sort of the first step down the road towards relativistic quantum mechanics, which is a deep subject in its own right, and it is rather advanced for a survey course of this type. And so our treatment is going to be specific but not very comprehensive. We're going to look at the original work of Dirac, who early on, just a few years after the Schrödinger equation was discovered, decided that he would investigate the extension of quantum mechanical ideas to make them consistent with the theory of relativity. The Schrödinger equation, you see, is a non-relativistic equation. It's based on a non-relativistic description of mechanics due to classical mechanics. So Dirac undertook to understand the nature of the wave equation for the electron in a relativistic form. So we're going to discuss just the equation for a free particle in one dimension to keep things simple. So here's the Schrödinger equation for a free particle in one dimension. And it's easy to find the solutions. I mean, basically, the solutions are e to the I p dot r divided by h bar, and then an e to the minus I omega t. With E is equal to h bar omega. So Dirac sought to find a relativistic version of this equation which would have the following very important feature. It would be homogeneous in time and spatial variables. You see, the non-relativistic equation is first order in time and second order in spatial derivative, and because of the Lorentz transformation, a fully invariant equation would have to be linear in space and time. And also there's a reason why you want there to be an evolution equation of this form. That is, you want to preserve the idea of a wave function, and you want to understand how a wave function evolves in time. So the only ingredients at your disposal are the momentum, which of course is P is equal to h bar over I d dx. So that has the right relativistic invariance. And then, there's a requirement. This is the relativistic dispersion relation, which describes the relationship between the energy, the momentum, and the mass of a particle. So you want your equation of motion to satisfy this relativistic dispersion relation. So possibly there should be another term here, which would then, if you look at this and think about it, you'll see that this does satisfy the conditions of relativity, provided that alpha squared and beta squared are both equal to 1, and that they satisfy this anti-commutation relation. Can you see why that is? Okay, so you can see that alpha and beta can't just be pure numbers. In fact, neither one of them can be an ordinary number because the anti-commutation relation has to be satisfied. But we're quite used, in quantum mechanics, quite used to using linear operators. And so, for example, here are choices of alpha and beta. These, you can choose sigma 1 to be alpha and sigma 3 to be beta. These are the so-called Pauli matrices. And this has a very straightforward geometric interpretation. So you're familiar with non-commuting operations. This one, in a two-dimensional system, reflects a vector about the 45-degree line, and sigma 3 here inverts the coordinates. So here's how sigma 1 acts, here's how sigma 3 acts. So you can see that the operation sigma 3, sigma 1 leaves this, whereas sigma 1, sigma 3 gives that. So that gives us an example of the fact that these mysterious non-commuting quantities can at least be mapped onto familiar geometrical representations. So, in fact, much of what we do now is not going to depend on choosing a specific representation for alpha and beta. First of all, there are many, many choices that give the same result. It isn't unique. It's sort of like the gauge invariance problem. What's important is that they satisfy the commutation relations. But if you choose 2 by 2 matrices, then it's easy to solve this, the stationary equation, Dirac equation. It's just proportional to a plane wave. And the remarkable thing is that you get both positive and negative energies. Now, you never get negative energies in the solution for a free particle in non-relativistic mechanics, because that would require an imaginary momentum, and it would give rise to a non-normalizable wave function. But as you're going to find in the homework, if you have a solution of the Dirac equation that's of positive energy, then you can find from it another solution that has a negative energy, and it has the same desirable characteristics of the positive energy solution. So there's nothing in the mathematics that says you can exclude the negative energy solutions, like there is in the non-relativistic Schrödinger equation. And these indicate the existence of antimatter. That is, these negative energy solutions have been found to be associated with the existence of antiparticles that are apparently present for all particles. Okay, so now another consequence of the Dirac equation, very significant one, is found, it's actually found in the two-dimensional and the three-dimensional versions both, but we'll go directly to the three-dimensional equation. So now you see this is a straightforward generalization of the one-dimensional Dirac equation. It has a contribution from each of the three spatial coordinates. And when you go and require that this relativistic dispersion relation be satisfied, you find that there's a class of anti-commutation relations. So the alphas have to anti-commute among themselves in the way indicated here. The alpha have to anti-commute with beta, and then beta squared is equal to 1. Now, this part seems fine, but what about the conservation of angular momentum? That's one of these things that you would surely wish to see conserved, but it doesn't commute with this Hamiltonian. I think that's quite easy to see because this has a form of a vector.